And you can see it's working. Sysvar. Whoa! Let's do an ls slash again. Let's do an ls slash bin. ls ls slash. What should we do? Woo! Um, ls slash. Yeah, let's do ls slash bin. Ooh, uh, no, wow, that's painful, but it's just amazing to see. It's interactive. 3, 4, 5, 6, 7. Well, you can count for yourselves. But just to explain, this is the BusyBox build route built by Paul McCarris, which you can see in, where is it? Shenki's instructions, shenki.github.io/boot Linux on microwatt. But here the difference is that I'm actually running it on under verilator. I'm running it's still running microwatt HDL under verilator, but booting the exact same Linux kernel that you saw in the RTA7 thing online. It's been published thing, but I'm able to do here we're able to do DTK wave VCD traces, and we're also able to do memory dump. A snoop on every load and store to the what I've called the block RAM, which is allocated of 512 megabyte, and which this initial RAM disk is booting from. So yes, really, it is just taking forever. It's not hung. The Here we can see the block RAM bram.dump is up to 6.1 gigabytes so far. Tel minus f bram.dump, and we should be able to see that as that's going. Ooh, slash bin. So it's arch ln ping ash dummy. It came up with a thing. I haven't got the brightness turned up on this half bright, brightish. Let me turn the brightness up a bit for myself, my own benefit. Dump came up, login, pipe progress, su, stty, base64, echo. These are commands that have been created by build routes. And you can see this. Let me pause that so you can see what it's doing as it's executing a console output. And again, what you occasionally see there, for example, that will be the Microsoft, the microwatt iCache reading its list of instructions, and then dout that will be writing to some addresses, not one FFTBFTT. Because remember, this is running from an initial RAM disk, completely from an initial RAM disk. So we can actually snoop the operation here, all the load stores, and see what the heck's going on. So yeah, that BRAM file, LSRH, the BRAM dump file is up to 6.2 gigabytes. You have to be very careful with the verilator traces things, because 30 seconds will create approximately a 10 gigabyte GTK wave VCD trace file. So this is why in verilator you can put options to request that the tracing be switched on at a certain point, and then start outputting multiple tens of megabytes per second, or I think hundreds of megabytes per second of signal traces. Oh, that's quite a lot there. The thing, quite a lot of commands. Uname, shown, grep, the thing, said. That's going to take a while, but this is absolutely fantastic to see. And our next step will be to write an equivalent of the various things that done here for microwatt, and do the same things in LibreSoc and use the LibreSoc core. Now we could use the VHDL, because what basically, if I have a look at the thing, where is it? VISOC.vhdl. We're going to have to duplicate this, which is the microwatt SOC. This is the HDL that you're seeing running here now. And you can see it's got things like a UART 0 and UART 1. UART 0 is what you're seeing this console output on at the moment. BRAM verilator access, that's what you're seeing, you saw from that bram.dump file, and that is from this file here. This is the code. It's within this loop. That read and write is what you are seeing being accessed here. Those signals, these signals come out, they propagate out all the way right the back way through. Oh, it's finished finally. It's done at LS. Is there a who am I? Who am I? I think let's leave that to run. Who am I? Ooh, yeah, what is it doing? Random fast init done. Oh, thank you for letting me know on the system console. So these signals are added when they propagate right the way down from the BRAM wishbone bus thing coming out to the thing. DRAM we're not using. We'd have to write an emulator for a DRAM if we would do so. The ZIX controller, you can see there. That's for interrupts. DMI, we're ignoring those at the moment. As far as this simulation, etc., is concerned. There's your this is a component exported by 1650 compatible UART from FuseSoc. So that's that's what we were seeing the UART console things on that. That's serial 0 or TTYS 0. Here's the processor. Woohoo! Oh, it responded. Who am I? Root. Cool, brilliant. So here's the, where is it? Where's the? Here's the core. The processor core. This is the microwatt core. And strictly speaking, technically speaking, what we could do is drop in a simple replacement for that only, because we do actually have, because of the work that I did previously, the external interrupt is there. I've got that signal. I've got a fully compatible DMI. The wishbone interface, yep, 64-bit. I don't have an out reset yet. I could add that. And obviously the reset and the system clock has absolutely no problem at all. Yeah, no problem doing that. It's all of the rest of the things, like this, the top interconnect. I think I've got to investigate what that's about. The slave IO latch. Yeah, all of these things are what I have to do. I would have to create a wishbone arbiter, a 1650 UART handler, drop in the ZIX bus, ZIX ICP and ICS onto that bus as well. We have to write a syscon peripheral, and that's over here. That's quite straightforward, actually. It's just, if um, just reporting all this information which comes through from the hash defines, which are part of the build process. So at build time, you specify this has, when you're building the actual Verilog VHDL, in the make file, you end up specifying, or actually not so much in the make file. Well, there are actually a few overrides of things. So if you have make file, so for example, -G, where is it? Oh, here we go. GHDL image generic. These are the things that are passed in from the make file to the VHDL macros, which end up as things here. So, for example, where is it? Clock frequency. Clock frequency is passed in to syscon as clock underscore freak, clk underscore freak, which gets turned into a 40-bit signal info underscore clock. And when you do a read of, I think that gets turned into reg clock info, reg clk info, and here is the wishbone read of the memory read of at this address. So when you read from an offset of 0xC000 plus sys reg clock info times 8, whatever it is, the information that is returned is reg underscore clock info, which is a way that the early bootloader gets to find out what the clock frequency is. And I'm kind of surprised that this information isn't yet in the Linux kernel, so that it can be substituted into the device tree file, because it's currently, that's clock frequency is currently hard-coded and duplicated here, and that's what caused the problems that we had earlier with the consoles. And if that syscon entry had been read and put into the read and substituted into the device tree entries, we wouldn't have had that problem. Also, things like that it could have noticed that the Ethernet is disabled in the configuration that we set up, and we could have avoided. I know it looks like it's only 3.5 seconds, but that was about an hour of real time. About half an hour of real time to just to discover that the Ethernet wasn't there. Yeah. So anyway, so that's back to that. So we've got to do a syscon. We'll have to this is in LibreSoc. We'll have to do the arbiter bus arbiter like this. So when you see certain addresses, I think, and this is what there's actually some libraries already for this in the HDL, in the Namigen HDL, which is specifically designed for this task, to give you this thing, so you don't have to spend huge amounts of effort on it. What else? We have to wire up the I/O, the interrupts in exactly the same way, and I'm delighted to see that the interrupts are in fact listed very clearly here. So we can just do interrupt UART 0, and as long as we have that go through to the 6-bit 0 of the 6, then we're good. Yeah. So this should be maybe about 4 days work, and we should have another report by then. The challenging bit is the reason why we did this in verilator. The reason why look, why isn't LibreSoc doing microwatt work is because we want to use the 1650 um, 1650 UART 1650, which is in Verilog. And it comes from open course, originally on LibreCourse. UART 1650 UART top.v, part of the 6.3 compatible project and open course by Jacob Gorban and Igor Mohol. Thank you very much for doing that. I mean, I know I do appreciate it was like 21 years ago, but it's absolutely fantastic. Visit work. Oh, great! It's under the LGPL as well, so that's good for us. That's absolutely brilliant. Really appreciate you putting that under that license. Um, uh, so we have to compile LibreSoc to Verilog, which means that we have to run a Verilog simulation, and the best one is Verilator. It's one of the fastest ones in the world that's capable of running, compiling Verilog and simulating it, and so that's why when you think, and we've got all of these pieces, a huge number of pieces. It's like having a multi-dimensional. It's a multi-dimensional version of the three-legged stool. Now that we've got to the point of running microwatt under verilator successfully, all we need to do is replace one leg of that multi-leg stool, swap out microwatt for the microwatt core for the LibreSoc core, and we're done. Whereas previously that would have been slightly problematic, trying to go, oh yes, we'll go straight to running a completely untested piece of HDL under a completely tested simulation system. No, I think you have no idea which thing would break. You got, the more unknowns you have, the more that the possibilities of things could break, and you don't know which one did the breaking. That's the problem. So by having this work, we can now just substitute one thing and one thing only in a known, with the rest of the things being known good. So that's all. It's really exciting thing. It should be extremely useful for other people who want to investigate open power systems. The ability to do the VCD traces and the memory load store dump would be hugely useful for investigating research and et cetera, et cetera. Thank you very much.